Hi, my name is Rami Buamer, and this video I will explain the backtracking problem solving pattern. Specifically, I'm going to focus on solving the maximum profit from stock trading problem from lead code. In this video, I will explain the backtracking pattern and demonstrate how to solve the maximum profit from stock trading problem in Java, and discuss the code, edge cases, and its time and space complexity. So let's briefly understand backtracking. Backtracking pattern is a recursive algorithm that explores all possible solutions by making decisions and undoing them when necessary. So the pattern explores every possible decision path recursively. Bruins path that violates the constraints or don't lead to optimal solutions and useful for optimization problems. This pattern could be applied to solve problems that has combinations and permutations, solving puzzles like Sudoku and N-Queens, and for optimization like what we have in my example, financial optimization. Let's go and see my example, maximum profit from stock trading. So I have stock prices over several days and I have only two limits transactions and I have to find the maximum profit by deciding when to buy, sell or skip. So we have prices like day 0, we have 3, 2, 6, 5, 0, 3. After doing all decisions, I have transaction 1. When I buy at 2, I sell at 6. I have $4 profit. Then I skip the next day. Then I buy at 0 and sell at 3. So the maximum profit will be 7. Here we have the backtracking recursive tree. And in this tree, we can see the nodes represents the state of each day. And in each day, we have the number of transactions and the profit, and if we can hold or unhold the position. So we hold only when we buy and we unhold when we skip or sell, like here. So these are the decision we can make, either skip, buy, or sell. So from the day 0, we have only two options, either skip or buy. And if we go buy, we sell what we have or to skip, okay? And at every decision, the state of the node will be updated. So that is the concept of this recursive tree. And as you see, it expands as we make other decisions, or if we have like multiple or more transactions, or if we have like more data of the prices, uh, more than like 6 days or 7, 10 days or something. So now let's go to the code that will implement this uh, algorithm in Java. So in the code, we have the class max profit, and the logic will be implemented in three pieces. Like in the main method, we have the function called max, this one, and this will calculate the maximum profit. We will pass the number of transactions and the array of prices here, like here. Okay, this method will be part of solution object, the object that we created here. We call solution. So this is an instance of the class max profit, and uh, then we print the maximum profit. Okay, that's the concept. So we have the method max. The max then will call a method called backtrack, and the backtrack is the method where the recursive process happens. Like here, we have three decisions: either we skip, buy, or sell, and we have the base case. Either uh, the days are done, like we have 6 days here, the length of the prices, or the number of transactions k also uh, done. So at the end, we return the profit. So as we said, this is like helper method. It's called in the max function here. So, and we pass the price, the day, the first day, the number of transactions. The first day we are not holding, so false, false. Okay, and uh, we don't have any money at the first, or we haven't buy any asset or stock at the first day. Then the third piece here, we declared the backtrack function. It has like five arguments or parameters: the prices, day number, and the number of transactions, the holding stats, either we hold or not, and the accumulated profit. So at first we go and check the node, the stats of node if we are finished checking the days, and then we start the recursive cases. So either we skip and pass the price, and the next day add like one to the current day, and always we hold on skipping, and we check the profit. Then we go to start uh, implement the buy condition. So on buy we have the condition not holding. So we do the backtrack recursively, prices, day plus one, and we deduct one from transactions because we have the limit of transactions too, and we are holding here because we are buying. So, and after buying, we uh, deduct like the price from the profit, the price of that day from the profit. And this is the logic of the sell. So we are holding when selling. So we pass price and we add the next day. The case stays as it is. We don't hold. So profit plus the price. At the end, we return the maximum profit, return the maximum. We call the max from math function, from math, yeah, function, and we pass the skip or buy or sell. That's returned in this function here, backtrack, and this function will be returned through calling the max uh, function here. So that's the logic of the uh, code that implement backtracking. If we run it, as we see here, we have 326,503. The maximum profit will be 4. If we change like some numbers like 10, we put here like 6, for example. So we buy at 1, for example, and yeah, let's check these numbers. So, okay, still here. Oh, we haven't saved this yet. So here we go. 4, still 4. So let's try. Uh, we buy at 2. Yeah, 4. Exactly 4. We buy at 2 and sell at 6. So that's 4. Yeah, and here we cannot do anything. So that's correct. So let's do, for example, 120. Yeah, 2 here. Or yeah, maybe. Let's see. Oh, save 19. You see, that's the maximum profit because we have 19 here. So yeah, that's all. Maybe we can try another one, like changing to 0 here, um, 2 here. I want something to like decreasing price. Let's do 10 here. 10 to, yeah. So we are kind of testing the, yeah, 4. You see, we buy here, hold, sell, $4. We are lucky with number 4. Cool. That's the code. So let's go back to our presentation. So as you have seen, the efficiency is exponential in terms of time complexity. So, you know, um, this kind of, we are choosing like 3 decisions per day. So every time we increase the number of decisions, the time complexity will increase. The same with space complexity, so recursion stack. Uh, so we can use memorization to catch a result, or we can convert to dynamic programming. That's to optimize the algorithm. So by backtracking uh, uh, to solve the problems, it works because explores all possible solutions, handles constraints like transaction limits, states like buy, sell, and skip, and it has some limitations like computation is expensive for large inputs because, as I said, if we have like more data of prices or we have more transactions, will be expensive to compute the problem by using this method. So we need to optimize by using memorization or dynamic programming for efficiency. So that's all, and thank you for watching.